So my name is Tomislav, and this is Dario. And today we would like to talk to you about asynchronous or synchronous monitoring of systemd services. So we are both working for the Apis IT, which is a mostly government-owned company, and they are responsible for maintaining IT systems of Croatian tax administration, custom ministries, and other government agencies like geo-services. So we have responsibility to the people. We have responsibility to our clients. Why? Because if something doesn't work, our mistakes or mistakes on our system influence the lives of the citizens in Croatia. For our part, receipts can be taxed, trucks can't pass the borders, or some young couple can't register their newborn. It's a new thing. So how to keep that under some control? We have signed service level agreement contracts with 99.9% availability through the year. That means what? That means that every month we have a right to 45 minutes of downtime. These 45 minutes of downtime also has covered regular work on services, which is not much by definition. So our services, if they are down, it will be heard of, and because we are a state-owned company, media will closely report on it. For those who doesn't understand Croatian, the customs do not work, and we have a problem. So by the SLA, we need to work on the problem as soon as possible. We need to be notified as soon as possible that the problem actually exists. So today's agenda: increase the capability of monitoring without the increasing the stress on the monitored system and central monitoring server. So, as you can see, there is a free lunch. It's too good to be true. There's always a catch. But in this example, there is no catch. Why? Oops, sorry. So, we'll talk about asynchronous and synchronous communications. Asynchronous describes objects or events that are not coordinated in time. The execution of one task isn't dependent on another. Types of communication where messages or information are sent and received at different times, and there is no need for immediate response. Everyday examples are emails, company newsletters, messengers, and in our example, monitoring queries every T seconds. Synchronous is the opposite. Objects or events that are coordinated and interdependent in time. Communication takes place in real time between two or more parties, and there is a need for immediate response. In-person meetings, phone calls, video conferences, coffee breaks, conversation, brainstorming. Orchestra is actually a pretty nice example where one block is needed and intermediate with another. So, how to do it? This is an example of asynchronous monitoring. We have monitor machine and we have monitoring system. Monitoring system is asking, is your service okay? Monitor machine says, yes, my service is okay. And he does that every T seconds. So, there is a problem. How do you determine that period? What is the best period for notifications? Why? Because if the T is too small, network is flooded with mostly redundant packages, or simply asking, are you okay? I am. Are you okay? I am. That is not optimal. So, this is a asynchronous monitoring example where we use Zabbix. Zabbix is querying the monitor system. Is everything okay? He gets the states, everything is okay. After the query, and let's say everything is okay is 1, there's a problem with service is 0, we have 0 after one of the queries. Okay, we got notification, we are working on the problem is resolved, but we do not know that until the next query. So everything is okay, Zabbix has notified us that the issue is resolved and changing the status in OK. But how often the queries are sent, that is for us to determine. But we have problems here. We cannot get instant notification without system congestion. Why? Because let's say the T is, in this example, 10 minutes. And the fault or the problem with service happens on T plus 1 second. So we will wait 9 minutes and 59 seconds until we know that we have a problem. That is too much. Because the later we see the problem, the later we can react to it. So we also have possibility of synchronous monitoring. How is that done? We have, again, monitoring machine and monitoring system. Monitoring system is just saying notify me when the service status changes. Monitoring machine will send my service is down, or will say my service is up. Simple as that. So we will talk about systemd services. Systemd services has more than 20 states, but these 4 is most important to us. Why? Because these 4 services will tell us if our service, these 4 states will say if our service is okay or not okay, and by controlling and being notified about these states, we can do something about it. The main thing we will use it is the systemd. Yes, systemd can do that. Why? Well, because systemd has PID1 in Linux, and it's the mother goose, mother hen of all services that are run under him. How? We'll do it by this. This is the example of synchronous monitoring. We'll prepare the system with installed Zabbix sender, and we will create custom one-shot service. This custom service will, when triggered by this custom service will be when triggered will trigger the execution of the custom script. The custom script here will send to Zabbix by Zabbix sender if the system, our service is in 0 or in 1. It will sell value which will mean something to the Zabbix system. Also, we need to edit the service that we are currently tracking. So we need to add on failure option for when we have service problem, and we need to have execute start post option added with bin bash. In this instance, we cannot use on failure option with notify service at service. Why? Because this is a Tomcat. Tomcat doesn't have root authority, and it shouldn't have root authority. So here, what is happening when we are queuing the service? We see that the service is failed. We see that it is triggering on failure dependencies and starting the notify service. It sees that it is failed, sends value 0, and the value 0 is sent by Zabbix sender to our monitoring system, Zabbix. And Zabbix has registered that there is a problem. It registered that immediately, which is very important to us when every second counts. So we are notified something is wrong. Please look at it. And now that we are aware, we looked at it. We saw the problem. We we deal with the problem, and then we're starting the service again. Again, Apache Tomcat has started, which triggers the execute post start script, and then it's changed from failed to activating, which will guarantee our value 1, and Zabbix sender will immediately send value 1 to Zabbix monitoring system, and our service will get resolved status. That way, we can instantly get notification about our services. So, synchronous with asynchronous, our conclusion is this is all possible because we have central person, we have systemd, which is notified instantly about everything that happens under him. So if we need instantly notification for service and time is of the essence, the synchronous monitoring is a way to go. So now I'll get Dario to continue this with C groups.
Thank you, Tomislav. So as Tomislav said, in the previous example, we had a systemd who has the knowledge of our system, but who also has the knowledge of our system instead of the systemd. It's actually the kernel. And with C groups, why the kernel has the all knowledge? Because he allows the process to actually to use some specific part of the RAM. And he has to track all of that. So he has instantly knowledge. He has the instant knowledge. It was the processor asked for some amount of memory, or it was the reallocate, or it was freed. So, thanks to the C groups, who was developed in 2007, thanks to the Google and the Android phone, they also developed something that's called memory threshold. There aren't much information on the web regarding the memory threshold, because it was kind of buried in the man page on the bare end of the C groups. But it actually says that we can actually create a memory threshold for the specific C groups if the all amount of the used memory has been passed for some amount of the threshold. And how is that actually been used? It's been used thanks to the event file descriptor, which we'll actually look further. But as I mentioned, that was in 2007, and C groups. That's all regarding the C groups version 1. And in 2015, the C groups version 2 came out, and this part of the comment was added to the Linux kernel code that memory threshold is overly engineered pattern and it should be avoided at all costs. But then again, we are at 2023, that hasn't been removed, and it won't be in all future because C groups 1, it's, as my guess, pretty much mostly used in today's systems. So the memory threshold will stay with us for a long time. So how does this work? We have an application in the user space. We have a closely divided, and this is the kernel space. And the main page said that we have to create an event file descriptor, and we have to create a control file descriptor, and we have to specify the limit in bytes. And we have to write that in the event control file in the sysfs, so in the specific folder of the C group. So what is then actually a control file? It's a file that it's pointing to the memory usage of, for our example of a cronny service. So what does the kernel do? Kernel reads that C group event control and notes that it has to create a C group notification event. So our main process in the user space is waiting for the event file descriptor signal, and it's actually in the blocked state. and it's waiting for the kernel to notify them. So it's actually not using any CPU. It's actually waiting for the kernel to remove it from the block state and to put it to be able to be scheduled on the processor. So the left one is waiting, and the kernel is monitoring and it's noting the usage, and when the threshold has been passed, it's actually notifying the process in the user space using the event file descriptor. And actually, the event file descriptor is a really nice way for the inter-process communication, and it's much faster than the commonly used pipelines. So, to monitor a C group, we need a sidecar process, which is mostly in the block state for most of the time, but that doesn't concern us because that doesn't add an overhead for our system. But there is a question how to set up threshold and what will be the purpose of that sidecar process. That sidecar process was notified that the threshold has been passed. But should we kill the whole C group, or what should we do? That is actually quite a hard question, because we can kill it, but what if that problem actually happens again? systemd specifies if we want to use it with systemd service, we can specify the memory max, memory high, memory low, memory min, attributes in the systemd unit file, and it actually has a one-to-one mapping to C group interface. But the systemd sadly doesn't have a memory high action, the script that will actually run if the usage has got to the memory high. So we have to have a sidecar process. But actually the question, how many of you actually use systemd resource controller? How many of you actually specify the memory max, memory low, memory min? Probably no one. And why is that? Because most of the time, one virtual machine, it's one type of the workload. If you have one virtual machine with bunch of the workloads, so we can say this heterogeneous. There is some databases, Tomcat, Nginx web servers, and it's really hard to predict the usage and the behavior in the future of those systems. And the containerized environment is really a neat example of that. So we have, for example, in the Kubernetes workers, we have one pod, two pod, third pod, fourth pod, and fifth pod. And there is a high memory utilization of that pod. And actually, what has happened, the memory usage was so high that it triggered a general out-of-memory manager on the kernel side of the whole worker. And then, actually, we don't know what will happen in that scenario, because the OOM doesn't guarantee that it will kill the mostly mean process. So we want to actually avoid something like that. But how? We have to evict some pod that is causing some trouble. For example, we can specify that we will allow for all pods to have to use 95% of all available memory. The Kubernetes actually has that. If you specify that eviction in the kubelet config, but it has the eviction monitoring a period of 10 seconds. So actually each 10 seconds it's monitoring that was the limit passed, was the limit passed, was the limit passed. And the memory usage can actually rise pretty high. And we don't want to end up in that 10 seconds with lost all workload from the worker. So we can actually use something that is actually turned off by default on the Kubernetes for some strange reasons. And it's actually kernel mem C group notification. And actually in default false. And if it is true, it will actually create all of that we see on the previous slide. It will actually create a C group notification. It immediately when it will pass the certain threshold, it will evict the most meanest pod to some other worker. So we can see from the code, if the kernel mem C group notification has turned on, it will actually start a go routine, which will actually be in the block state. So in the previous example, we don't have a boom with OOM. It will actually simply evict pod to another worker when it will actually keep all our other workloads intact and pretty safe. So this is something that we want to achieve, and it's actually pretty neat that it's actually possible. So thank you for your attention.